Good evening, sir.
Hello. Hi.
Ah,
Hi, all. Hi, madam.
thank you, sir.
Yeah.
Thanks for
I'm
joining.
audible, right? Okay. No problem.
Shall we start, sir?
Yes, we can start.
Wait,
I
sir.
will
Wait.
share my screen.
So wait, sir. Wait a few minutes, sir.
Okay. Yeah.
Good evening, everyone. Welcome you all to the second day of the FDP. It is my great pleasure to introduce our distinguished speaker for today's session, Dr. Akhil Jose, a highly accomplished system engineering professional with vast experience in model-based systems engineering, functional safety, and autonomous vehicle technologies. Dr. Akhil Jose is currently serving as an associate technical architect at KPIT Bangalore, where he leads the MBSE squad for each access domain in a software-defined vehicle project in collaboration with the Renault Group. In this role, he is responsible for overseeing the delivery of system engineering artifacts while ensuring compliance with industry standards and best practices. His leadership extends to managing cross-functional teams, coordinating with global stakeholders, and implementing cutting-edge methodologies in automotive system design. With over 6 years at KPIT, Dr. Akhil Jose has played a pivotal role in multiple high-impact projects, including the development of L4 autonomous vehicle systems, automatic parking systems, and emergency maneuvering features. His contributions span concept development, functional safety assessment, and creation of MBSE artifacts using tools such as Enterprise Architect, Simulink, Polarian, and DOORS. Before transitioning into the automotive industry, Dr. Akhil was an esteemed academician serving as an assistant professor at Adi Shankara Institute of Engineering and Technology and Vimal Jyoti Engineering College. During his academic tenure, he was actively involved in research and development, curriculum design, student mentoring, and faculty coordination. His research contributions include studies on vehicular adaptive cruise control, PID controller optimization, and robust control strategies for nonlinear and unstable systems. Dr. Akhil holds a Master of Technology in Control Systems from Manipal Institute of Technology. To further enhance his expertise, he has pursued specialized certification in deep learning, sensor fusion, enterprise architecture, uh, he has pursued and digital twins from prestigious platforms such as Udacity, EDX, and LinkedIn Learning. His dedication to continuous learning and innovation has made him a key contributor to the evolving landscape of intelligent vehicle systems and continues to drive advancements in system engineering, automation, and safety technologies. We extend our warm welcome to Dr. Akhil Jose. Thank you, sir, for joining us. We welcome you to this meeting. Sir?
Thank you. Yeah, thank you. Thank you for your words. Yeah, thank you.
Thank you, sir.
Hi, all. Yeah. So we will start with the session.
Okay, sir.
Yeah, I will share my screen. Yeah, let me know if you can see my screen.
Yes, sir. Screen is visible,
Okay.
sir.
Okay. I'll start then. Okay.
Okay, thank you, sir.
Yeah, thank you, ma'am, for your kind words. Okay. Yeah, and thank you for the opportunity and welcome everybody to the session. So today we will be talking about you know, predictive maintenance, machine learning applications for predictive maintenance and fault detection in automotive system using digital twins. So first of all, my name is Akhil Jose and I work for KPIT Technologies as associate technical architect. So KPIT is a company which provides software solutions to OEMs and tier ones. And here I work as a system engineer in ADAS practice. So it is ADAS practice is for autonomous driving, driver assistant features and chassis systems. So currently located at customer location in France. Then I work in system engineering MBSc and currently also working on implementing artificial intelligence in system engineering. So yeah. So we will talk about predictive maintenance and fault detection. So these are the topics that I'll be covering today. One is introduction to predictive maintenance and digital twins and importance in automotive industry, how this plays a major role in automotive industry, then different machine learning techniques that are used and digital twin integration. Then use cases, we will be talking about multiple use cases, which we are, some of the examples. And here I would like to say I won't be going in detail in all the use cases because what I try to do is I try to bring a lot of information into this PPT. I try to collect from different domains which I am not working in. So some of the application I'll be able to go deep, which we will be specifically taking one use case and we will be seeing like end to end on that particular feature. Otherwise, I have mostly kept the features so that if somebody is interested, maybe like the feature which I am talking may not be relatable for you, and the technique which I am going to talk also may not be relatable to you. So in that case, the other slides you can refer and you can get an information about it. So that is the intention of keeping like multiple use cases. So I tried to compile different applications so that you can take and refer further on those applications. So specifically EV battery health monitoring, I won't be covering in detail. And again, commercial fleet predictive maintenance also I won't be covering in detail. But engine fault detection, I'll be covering in detail. Yeah. Then challenges and future directions, then conclusion. Yeah. So when it comes to predictive maintenance, yeah, so it is a proactive maintenance approach. So even before the actual error has occurred, we are trying to proactively uh, resolve the issue or identify the issue. So by doing that, we will be optimize the maintenance schedule and reduce the downtime. So maybe like the by the term itself, people might be familiar what is predictive maintenance. We are trying to analyze the inputs that is coming from the vehicle and we are trying to understand whether we need to go for a maintenance or some failure that might occur in the future. So and digital twin is again another concept where we maintain a virtual replica of the actual physical component, and based on multiple inputs we train the digital twin. And in some cases, in the future cars, what we will be seeing is we will be getting information from IoT sensors and we will be monitoring the IoT sensors in real time, sensor data in real time, and we will analyze that and make the prediction. So nowadays, one major change that we can see in automotive industry is about the use of lot of information. So currently, the project that I am working also is about software-defined vehicle. So it is, our mobile, the vehicles are also going to be like our mobile phones. So if you want some feature, upgrade your vehicle, what is going to happen is you will be installing or like subscribing to some features. You will be installing some software and you will be able to use an additional feature in your car. That is how, the feature is going to be. And at the same time, same like how in our mobile information is used by different companies. From car also they will be collecting a lot of information, obviously for business reasons and for improving the user experience. So here one of the application is it may collect a lot of information from your sensors and use it to feed the digital twins and see and identify the anomalies and give a uh, prediction for predictive maintenance or any other alert. So what is the importance in automotive industry? So one is minimizes unexpected breakdown, which we already taught. So we may be able to predict before a failure occurs. Then extend the vehicle lifespan. So if we are able to do the maintenance then at correct time, then you will be able to increase the longevity of the vehicle. Then enhances safety and reliability. Definitely, if there is no failure, unintended failure that occurs, there will be safety, more safety and reliability. Then reduces maintenance cost. So if we are able to identify the errors earlier, we will not be able to. We don't have to face lot of wear and tear. If we are running a fail vehicle with lot of failures, then it may lead to increased maintenance cost. So this is how machine learning comes into picture in digital twins. So previously also there were talks on digital twins where we uh, use data intensive uh, processes to train the digital twins. So now machine learning is playing a major role. So we have a lot of data. One of the advancement in machine learning is the use of deep learning and transformers, which needs a lot of computation. So that is how the current trend is going towards. And now the machine learning with the availability of a lot of data. For example, we have IoT sensors. So with IoT sensors, we will be able to gather real-time data, lot of real-time data. And since the amount of data that is collected now with good internet speed, good connectivity, and lot of parallel computing power, these data can be processed to train the models. Train the models. First, we will create a model, then we will train the model, and we will use the collected data, real-time collected data, to give predictive insights to the customer. Then key of AI in role of AI in predictive maintenance. So key contributions of AI, one is data analysis, how AI is contributing to predictive analysis. So predictive maintenance, one is data analysis, then analyze large data set to identify patterns and anomalies. We will see some of the examples. Then machine learning. So again, the way we perform the analysis has improved a lot through machine learning. Then natural language processing. So how we interpret, that is another advancement. We all might be using this chat GPT and all the large language models. So that has really come out to be more intelligent than how it was before. So we will be able to interpret the error and you know interpret the maintenance logs and give suggestions to the customer in a way it is a customer service person is interacting with the customer. Then reinforcement learning. So we will be able to optimize the maintenance schedules. So if you have any doubts or if you want some clarity, you can interrupt me in between as well. If I'm able to clarify, I'll be happy to clarify. Then technical foundation, that is another point I would like to address, that is like data pipeline. So now, as we discussed earlier, there are a lot of data available, sensors available. Then some of the data may be collected during service through onboard diagnostics or telematics. So telematics is also now a new thing. Now your data will be collected over the air. That's how it is happening in a mobile now. Hmm? So this way we will be able to do a real-time monitoring of the vehicle. So this is the most effective way, and in future it is going to be mostly telematics. Then cloud processing, definitely we need to do the processing, faster processing. So mostly we will be relying on the cloud to do the processing. So most of the parallel computing, processing, GPU, everything will be hosted through cloud. Then feature engineering, definitely we need to identify features or extract the feature from the inputs that we receive. So this is the technical foundation. Then what are the different types of machine learning techniques used? So there is supervised learning and unsupervised learning. Obviously, like everybody might be knowing about it. So in supervised learning, we use give me 1 minute. Give me 1 minute. I'm facing some issue with my laptop. Yeah. Okay. So in supervised learning, there are multiple learning methods. One is classification, another one is regression. So in classification, there is supervised learning. It is, I think most of the people might be aware. Yeah. So supervised learning is like how we humans learn or how we teach. Like for example, if we how we teach a kid, like you show a photo of a cat and say this is a cat. So we should have labeled data set. So we know in the data set what is what. And we try to learn a machine, try to make the model which we have, or digital twin which we have created, aware of the data set which we have created. Then another one is regression. So here, again, what we try to do is we try to predict the remaining. See, we try to get the data, continuously get the data, and based on the data, we try to identify from each data, we will be able to kind of predict the next data. So the application of this kind of analysis or learning is, for example, if we are considering an engine's case, we will be collecting the data from the engine. And based on the data which we are getting, we know how the degradation is happening in the engine. So we will be able to predict the remaining useful life for a uh, particular sensor or a machine. Then there is unsupervised learning. So unsupervised learning here, we don't have a labeled data set, but this is also kind of, so most of the machine learning technologies now is kind of, mimicking human behavior. So here also, even though it is an uh, unlabeled data set, here we are trying to identify what kind of patterns we can recognize in a unlabeled data set. For example, see, humans are also capable of doing the same. If we are given, few different patterns, and if we are asked to identify which pattern is not matching with other patterns, we will be able to identify. So similarly, in a given data set, the unsupervised learning will be trying to identify the anomalies. So here also we have multiple techniques like autoencoders, reinforcement learning. So in autoencoders, what happens is, for example, we will come to such examples in the coming slides. So reinforcement learning is also one technology that is kind of a reward-based learning approach where we will try to optimize the maintenance policy or like try to reduce the loss by what you can say a reward policy, reward or penalizing the output. So that is also used to control the automotive in large way. So it is used for autonomous control also. So this gives a key difference between different techniques. So supervised learning will be used when you have a labeled data set, and unsupervised will be used when you don't have a labeled data set. So these are some examples given. Then reinforcement, if you want to optimize actions over time. So yeah, we will see some examples in the coming slides as well. What happened?
So please mute your mic.
Yeah, okay, we'll continue. So digital twin integration. So how a digital twin is integrated into the system. So what we do is we mostly have, so how digital twin exists in a company. So we will be using a simulation environment. So a model may be created. It can be created using a simulation tool like ANSYS, MATLAB, Simulink, or it can be in a deep learning network that is created. So a model is created, which is model to have model to know the behavior of a machine. So that simulation environment is created, and then it gets the data from the sensors. So this model will be learned based on a lot of data. So machine learning, what how it is done is it is already learned with lot of inputs and outputs, and it knows for each input what will be the kind of behavior an engine would be exhibiting, or like if an engine is in failure, what will be the input it is having, or like for what kind of input we should predict it as a failure. So we will then, once that learning is completed, we will be getting the information from the real-time data, and based on this, again it learns as well, it gives prediction. So we will go through some automotive examples with machine learning techniques. So yeah, I'm also not aware of all the techniques that is mentioned here, but yeah, whichever I am aware of, I will discuss. Rest of the things like you can explore as well. So one of the use case is autonomous vehicle sensor health. So here, nowadays vehicle uses a lot of sensors. For every application, you need sensors. Now, see, if there is a failure of any component, sensors will pick it and give it to us. Or else, if there is a ADAS operation, autonomous driving operation, there are a lot of sensors that are needed to give the information to the autonomous ECU to process and drive autonomously. Mhm. So this particular example is for autonomous vehicle. So here the sensors used can be lidar, radar, ultrasonic sensor, camera, or inertial motion units. This is definitely needed. So these are the sensors used in automotive vehicles. Mhm. So this gives the direction. So based on this input, the autonomous vehicle should be able to assess the environment, like how we use our sensors to identify what is happening in the environment. These are the sensors for an autonomous driving vehicle. And this information is fed to machine learning model. Mm. So this particular example, where it uses an auto encoder to detect sensor drift anomalies. So what an auto encoder does? Auto encoder we already discussed. It is an unsupervised way of learning. It didn't learn the information based on like some trained data set. It is it is this particular machine learning model tries to identify the anomalies in the pattern. So what it tries to do is it tries to autoencoder. What it does is it compresses the data and reconstructs the data. Hmm. So when it compresses and does an analysis, compresses, like first it gets an image, then it compresses and it reconstruct the image. So when it reconstruct the image, it will analyze the reconstructed image, and if there is the data is not proper, if the reconstruction gives anomalous behavior, if you are capturing an image of environment, it will have a specific pattern for the pixel. Hmm. If we are having some dirt on the camera, hmm, when we compress and reconstruct, it will have a different pattern of the reconstructed image. So based on the reconstructed image, we will be able to, or the camera or the machine learning model will be able to identify this particular case is a anomaly. So in such cases, it will alert the driver to take action to clean the sensor to continue the autonomous driving, or else it will cancel the autonomous driving. And nowadays there are some applications where sensor cleaning, automatic sensor cleaning is also deployed. So it will spray water or wiping technologies to clean the sensor as well. So again, this data can be verified. So this is like this reconstructed data gives an idea whether it is an anomalous behavior or not, and this can be verified by a continuously running simulation. Continuously running simulation. So this kind of whatever information is provided can be directly simulated in a This Carla is a simulation environment where you will have a car and car will be using different sensor data to run in a simulated environment. So by using this information, the simulation can understand the sensor failure because it will understand it's not getting the correct data. For example, in the simulation environment, there is a camera, speed sign, and if it is the sensor is proper, it should detect it. But if it is not detected, such things it can identify. It can identify the anomalies in behavior, and based on that, it can give feedback to the driver in real time. And another thing is HVAC, so heating, ventilation, and air conditioning system in electric bus. So here, these are the things that is monitored. One is temperature, so real-time thermal profile tracking across the passenger compartments. So, what is the temperature profile in each compartment? Then airflow dynamics. So based on the airflow from the vent, it will be able to understand. So there will be sensor to identify that. So based on the airflow, it will be able to identify whether there is a filter clogging or ventilation. What is the ventilation efficiency? So all these things it will be able to predict by measuring the airflow dynamics. Then there is energy optimization. So intelligent power consumption management for HVAC. So we will be able to measure the energy utilization. So all these factors affect the efficiency of HVAC system. So here the technology used for this particular application is support vector machine. So this is one of the initial machine learning approaches. So here it tries to do is it tries to uh, classify different features. So it tries to fit different features into different categories. So we'll not go in detail about support vector machine. So maybe like some people might have already worked on support vector machine. So yeah, if you're interested, you can explore. So this is one of the application. Then another thing is real-time MQTT. This is a communication protocol. So this kind of communication protocol this is for telematic operations. So the data is directly transferred to the server, and from the server, the electric bus can receive the alerts from the server. So this MQTT protocol is used to update the maintenance schedule. So the protocol will there will be a maintenance schedule that is nowadays in our cars also we can see maintenance in these many kilometers. That is set based on the amount of the number of kilometers that we covered or the number of dates days passed. So that can be updated in real time based on the efficiency of the activities that is happening. So by making the measurement and analysis, this MQTT, using MQTT protocol, we will be able to show in the dashboard that your maintenance is scheduled in these many kilometers. So based on all these data, it will be able to understand, you need to change the filter or make some changes in battery or temperature is increased and you have to go to service in like 1,000 kilometers or 1,500 kilometers. That is the kind of prediction it will be able to do. Then another thing is brake system anomaly. So this is like currently in my project also there is a predictive maintenance approach, but that is not machine learning and all. It can be achieved without maintenance. It's not predictive maintenance is not always machine learning. See, for example, the same use case which I have used here, brake pad. So for brake pad, nowadays there are a lot of sensors in the market. When the brake pad lining has worn out more than a particular amount, it will establish an electric connection. And that will show us an alert to the driver. So that is a method to show predictive analysis without machine learning. But here we are talking about machine learning. So here, like, the information that they uh, receive is accelerometer, hydraulic pressure, brake pad thickness, etc. Then random forest uh, classifier. So this kind of identifies different anomalies or like abnormal patterns in the braking. So for example, if the brake pad thickness, so it will be measuring the brake pad thickness, and if the brake pad thickness is below a given threshold, it will be able to identify it as a failure. Then 1 minute. Yeah. Yeah. So here what it tries to achieve is like, it will be able to identify the abnormal braking pattern. So it will measure different parameters like hydraulic pressure or accelerator or accelerometer, or so accelerometer gives the, acceleration data or velocity, all those things. So based on measuring all these data, this digital twin will be able to predict, abnormal braking patterns. So this information is enough to understand whether the, braking is going to fail, or like it, whether it is making an abnormal braking. So due to abnormal braking, it can cause severe harm to the vehicle and the longevity of the vehicle. So in such cases, the model will alert the driver to take action. Now we will go to some use cases in detail. 1 minute, my screen is stuck. Give me 1 minute. Yeah. Yeah. Okay. Okay. Yeah. I don't know. So this is one case study, but I'll not be going into detail of this case study, but we will take another case study to go in detail. So this is one, major application for EV health monitor, and this is one application where a lot of growth is possible because we know the, future is going towards EV. So now we are seeing kind of a plateau and kind of a reduction of EV cars, but still not reduction, but kind of stabilized growth. But in future, definitely like, better technologies like faster charging and longer mileage, EV is going to be a major player in the future. And even if it is hybrid, there is again like electric battery will be playing a major role. And standalone EV also is going to make a, large comeback, is what, the market trend is showing. And based on the current development that is happening, like, 20 minutes or 10 minutes charging is possible. Such approaches are being developed. So here what happens is, it measures uh, state of health of battery. That is one parameter that we will be measuring. So here what they use is voltage, temperature, and current. And long short-term memory is the technology used. This is a recurrent neural network technology. What it does is it predicts the next state, using a time series data. So based on these information, it will try to analyze. So it will be learning the machine. First, we will create a model and we will learn the model. We will try to teach the model about, how for different data, what will be the output. A similar exercise we will see in the next section, but the technology is different. Here, the technology is RNN, that is a recurrent neural network, and the specific technology in RNN used is long short-term memory. So here we are identifying, based on the current data, we are trying to predict the next state. So by you doing this, we will be able to identify whether there will be a failure soon or the state of health of battery is deteriorating. So this LSTM technology is kind of comes from the same family of technology. It's like RNN. So this is kind of technology that is used for language predictions. So for example, in like our mobile phone, or the previous models of translation, how it worked, where language translations, how it worked was using RNN, or else predicting the next word. Though RNN was used for natural language processing in such case. So similar principle is used here. So based on the input data, it will predict what will be the next state. So this way we will be able to predict the next state. So this simulates the digital twin. What it does is it takes a lot of data. Previously, like available data, sensor data is provided to digital twin to make the twin learn about it. And once it is learned, once it is learned, this data model will be used to analyze the present sensor data that is coming from vehicles. So based on the sensor data, the digital twin will tell, the how long your vehicle can run with this battery, or how much the battery degradation has happened already. So this way we will be able to alert the driver or the user to replace the battery. So this will not cover. Yeah, this is the technology used, and this is the architecture used. So this technology will not go in detail. I have also not worked on this in any way. So, but I know the basics of RNN and LSTM. So if somebody is interested on this, this is the architecture used, and they may be able to understand it, understand how the work is happening. But similar exercise we will do for another application. So maybe we will switch to that application. So again, this is different steps that is happening in EV battery, EV health monitoring. So what kind of data is collected and what frequency of data is collected and how the data is collected. It can be through from the CAN bus directly or like onboard diagnostics or from telematic system. So telematic system, as we discussed, is like, on the air transmission of data. Then there is noise filtering, like different types of noise filtering. If some data is missing, we will be doing linear interpolation. Mm. Then normalization. So, we need to bring the data into a scalable range. Then feature engineering, we will try to analyze time domain or frequency domain data. We will extract. So some of the pattern will be yeah, some of the pattern will be visible or like more understandable in time domain. Some of the features will be more visible in frequency domain. So we will do feature engineering here to extract different features. Then data splitting. So this is to train and to see what is the outcome. So to train, we will use some data. To simulate, we will to validate, we will use the rest of the data. So this is some outcome. So this is a specific case study that I have taken. So if somebody is interested, they can, use the tools. These tools are available for free, and I will be demonstrating one of this kind of application in the tool itself, not in the actual tool that is happening used in industry, but yeah, the tool where we can explore and we can do the actual work. We can understand the actual work. So you can do it in TensorFlow, that is free. This is not free. This is actual microcontroller. Then it is PyTorch, that is also free. AWS is not free, but yeah, that is for again processing. So this is something we will go a little bit deep into. So here, we are trying to identify engine fault detection. So here, what we are trying to identify is detect misfires. Oh, sorry. So detect misfires. Is there any wear and tear in the bearing, engine bearing, or fuel injector faults in internal combustion engine using vibration and pressure data? So here we are not getting any of this data directly, but we are just analyzing the vibration and pressure data. Hmm. So we have different sensors, vibration, oil pressure, RPM. So all this information we will have. Yeah. So these sensors are already mounted. We will get vibration of the engine, oil pressure, and RPM. Then the model used is one-dimensional CNN, convolutional neural network. So convolutional neural network was one of the most successful neural network deep learning technology that came across during 2030. When deep learning was in rise, this was one of the technology that was widely used for image processing and image and video related activities. But here it is one-dimensional convolutional neural network. But intuitively, it is easy to understand using image, two-dimensional convolutional neural network. So I'll show some example of two-dimensional convolutional neural network also. So here the data, what we are trying to analyze is vibration. It is a one-dimensional signal. So vibration will be like a frequencies, signal with frequency. So it is a single dimensional signal. So here it will be transformed to extract feature in domain to detect misfire. So that we will see. Then we will have a digital twin. That also we will see how we create a very small digital twin of our own. Then engine fault detection. So this is the data pipeline, how we are going to work. So here we have triaxial accelerometers, from the IMU sensor, inertial motion sensor. Then there is oil pressure sensor and RPM from the engine. Then sampling rate. Well, here in the case study, it was 20 kilohertz. It can be different also. Then pressure is measured with 100 hertz. Then data source is from engine ECU. So, the sensor data is not directly taken for analysis. It is given to ECU and ECU converts the raw data into readable, measurable units, and then it is sent to uh, sent to the digital twin for analysis. So here, the measurement will be happening in number of magnetic pole change or number of encoder decoder or number of infrared line passed through grooves. If you're circulating gear, how many times the gear has passed the what you can say and infrared line, that also can be a measurement how the sensor is measuring, but that is read by the ECU and converted into a measurable unit like acceleration or like vibration, which can be measured in SI unit. So that is converted in the engine control unit and that is sent for analysis. Then we will do pre-processing. So we use wavelet transform. So wavelet transform is used to filter out the high frequency noise. Then we will be splitting vibration signals into 1 second window. This also we will see. Yeah, we will not see. Yeah. So this is like, see, this is for analysis. We are segmenting the input. So we are taking 20,000 sample per window for analysis. So each 20,000 sample will be considered as one data set. Then normalization again, to bring the data into a scalable unit. We will normalize it between a range. Then feature engineering. I'm also not much aware of this root mean square. Like, to extract the feature, we are using a root mean square, I'm aware, but yeah, we are using, multiple feature engineering in time domain. However, we can get the feature enhanced. In frequency domain, we are using FFT to peak 50 peaks at harmonic frequency. So at harmonic frequency, the features, some of the vibrations get enhanced. So again, in continuous wavelet transform, scalograms is used in time frequency domain. So these feature engineering is used to enhance the features or extract the features, specific features from the signal. Then data augmentation to simulate. So this is used to simulate the real world variability. So while learning, we may introduce some level of Gaussian noise to simulate real world variability. So in the actual world, there can be some variation from the actual signal. So from the data set created, it may introduce some level of variability. So this is the algorithm that is used for machine learning model. So one-dimensional convolutional neural network is used. So why CNN? It extracts spatial patterns from raw vibration signal. So we will see this and then we will go to little bit of two-dimensional CNN also. So in architecture, we have input layer. Input layer consists of 20,000 as 20,000 samples in one signal. So that is what we segmented. We segmented 20,000 samples, 20,000 points into one signal. That will be one signal. Then we have different convolutional layers. We will see what are convolutional layers. So many people might have already worked on convolutional neural network. So they may be aware as well. For those who are not worked, this is the layer, we perform convolution. So we will see what is convolution also. Then there are two convolutional layers here. One is with 64 filters of kernel size 64. We will see what are these terms. Then we perform max pooling operation. Then again another convolutional layer that consists of 128 filters and kernel size 32, and an activation function, a ReLU. That also we will see what is this ReLU activation function. Then we perform max pooling. Then we perform max flatten operation and dense. Then there will be output layer and a soft max operation will be performed. That also we'll see. Then there is a terminology called loss function that also we will. Then there is optimizer. So this is used for learning. So if you have worked on any level of optimization, you may be knowing about loss function. So loss function is a function which we try to reduce. So consider this as a loss, like the variability from the nominal value or variability from the actual value that we need to achieve. Or like an error, we can consider it as an error. So we try to reduce the loss function. So there are different technology, gradient descent algorithm, or like there are multiple algorithms that is used. So we try to make different changes in the learning, so that we will try to reduce the value of this law function, that loss function. So that is the entire idea of machine learning model, to reduce the loss function. Then we use an optimizer to start learning and reduce the loss function. So we will see these things. So we will go to one-dimensional convolutional neural network. So what it does is, a convolutional neural network will be able to extract spatial features. But one thing I would suggest is a little bit of neural network knowledge may be needed for this. I may not be going in that detail now. If you have some neural network knowledge, this will be kind of easy to understand. But otherwise, also you can use this data to, I'll be sharing this information. So you can use this information to learn about, neural network and revisit this slides, and I'll be sharing some other files also. So what a convolutional neural network does is, it tries to extract spatial features from any signal, any given signal. So we will see. So before going to this, maybe we will try to see how it is done. Yeah. So this is a two-dimensional neural network example. So hope you are able to see browser now. Yeah. So this is how a two-dimensional neural network works. So we will see. So it has multiple operation, as we discussed earlier. It has multiple operations. Again, I will go back. It. Yeah, as we were discussing, there are multiple operations that are happening. One is like convolutional layer. In that, there is filter. Then there is, an activation function is used. Then there is max pooling and different activities, flatten, dense, all those things are happening. So yeah, we'll come back to this later. So this is how, you may be familiar with the term convolution. Everybody may will be, convolution is kind of, a filter is, or like a value is convoluted over another value. So it is kind of a multiplication, a sliding multiplication. So this is kind of convolution, we can say. So, we place a filter. So this, consider this as an image. So I am telling two-dimensional convolutional neural network here. One-dimensional will be little bit less interesting. So we will go into two-dimensional, you know, convolutional neural network. So what we do is we do a convolutional operation. So we create a filter with here it is 4 by 4. It can be 3 by 3 or any size. So this is 3 by 3 kernel or filter. So it can be 1 by 1 also. 1 by 1 doesn't make much sense, but yeah, this is 2 by 2. So consider this is 2 by 2 filter. So each column of this, gray color, what you are seeing is the actual image. Consider it is the actual input signal. And the pink color, what you are seeing is the filter that we are using to convolute these two things. So this is the filter 4 by 5 kernel we are using as a filter. So what it does is it multiplies the behind value and adds all the value. So this is the operation what is happening. Each kernel, each column in this kernel has a particular value assigned to it. So that, and the below, okay, that I didn't say. Okay, so below part, you can see a big picture here. Consider this is a picture. So every pixel, if it is an image, you can consider this as pixel. So each pixel has a value to it. It can be from 0 to 255 in case of grayscale image, or it can be between 0 to 1 also if it is normalized. In our machine, the engine case also, it will be a large signal which is between some range. So it will be having some value 0, 1, 2, 3, or 0.1, 0.2, 0.3, 0.35, like that, some values. So this image also may be having the underlying image will be having some values in each column. And the filter also will have some value assigned to it. So these two values are multiplied and added together and put into a new column. So this is convolution. Hope it is little clear, but anyway, you can go through and understand this, or there are a lot of videos available to understand this. So again, convolution is sliding and multiplying. So, these 4 columns are multiplied and put the value in the single column in the output. Similarly, it is sliding to the next position and does the same operation. It continues to do like this. It continues to do the operation like this, and like this. So now the input was 5 by 5, the image was 5 by 5, the output is 4 by 4. So this is how we can do a convolutional operation. So hope this is clear. This is the convolution that we talked about. So this is a convolution. This is what happens in a convolutional layer. So here you can see, this is a cup with some espresso or coffee inside that. So what is the idea behind convolution is, for example, if you are multiplying, doing that convolution in this area and multiply, this is the filter. This is a filter having some value minus 0.25, minus 22, all these values. This filter is multiplying here and putting the value here. So this multiplication is happening and putting the value here. So if you see, some multiplication is happening here and putting the value, but there won't be much variance in value because, the background, the filter value doesn't change at all. And the image is having the same color in this entire area. So we can see here also, the multiplied image also will not have any variance. It will have the similar value. But if you see, and again, if you are, checking in this area, cup area, again, there is no variance. So, it is multiplying and giving the same value. But if you are multiplying in the edge, when the transition is happening, there you will see a lot of change that is happening. So when the filter is coming here and multiplying, it multiplies, adds and add the value to the output. So the edges and all the features, distinguishing features, from the background gets enhanced. So all the distinguishing features gets enhanced. So that is the idea of convolution. So that we can understand like what is convolution. But beyond that, what is happening and how the classification is happening, we can intuitively understand, but 100% understanding, it's not possible because it is like in deep neural network, maybe like, this is kind of the first model, like, where we stopped understanding what is happening inside, machine learning algorithm. So then also now here in this case, at least we can intuitively understand what is happening. But when it comes to the recent models like transformers that is used in large language models like ChatGPT and all those things, it is almost impossible for us to understand what is happening inside, but we have the intuition what is happening. So what is happening here is, we do that operation. So that is one operation. Convolution is one operation. Then what we do is, we have some other operations that is done. So we have an activation function. So what this activation function does is we, multiply the pixel with or pixel or the output that is coming with the nonlinear function. So it has two application. One is to introduce nonlinearity so that, the learning will be more biasless. It introduces a nonlinearity. Also, it brings the normalized signal in a range. Hmm. So this is a ReLU that is used as one of the activation function. There can be multiple other as well. There is something called sigmoid activation function. And for the new learning models, there is another iLew or something is used. So this is ReLU, that is one of the commonly used activation function. So this is multiply to introduce nonlinearity to the output. Yeah. So why maybe like, we will not go very deep into this, but yeah, anyway, like some of the terms needed for our application we'll be discussing in the slide. But I'll tell what is happening here. So, we are trying to assign weights to these connections. Some weights will be assigned to each of these connections, what we are seeing. So here you can see it is one convolution is happening here. So yeah, this is a picture. This is a supervised learning that is happening. So supervised learning, we said there is a labeled data set. We know what is what. So so here if you see these are labels given. So here there are so many inputs. There is a picture of bus, there is a picture of orange, and there is a picture of cup. So cup, this is espresso, not cup, this is espresso. So here there is labels given. There is espresso, there is cola, there is school bus, there is orange. So first we will train the model with a lot of information. So what it does is it performs convolution, then it multiplies with the activation function, then again it passes through a convolutional layer. Then again it multiplies with another activation function. Then it does a max pool. Okay, max pool also we will explain. So max pool. Okay, max pool. I don't know. I'm not finding an image. But see, in max pooling, what happens is it takes a oh, again it is getting stuck. Okay, what is happening is, see, we take consider this is a filter. Again, we are using a filter in case of max pool. So we take a 4x4 filter. So in max pooling, what we are doing is in that four different values, we take the maximum value and put it in the output. So the entire dimension of the input will reduce to a smaller amount, but the maximum value is retained. There are different types of operation that exist. One is max pooling. There is average pooling. Average pooling means takes the average of all the four values and puts into the output. So in max pooling, what is happening is we takes the maximum of the filter, underlying value of the image in that filter and gives it to the output. Then again it passes through. So the image size has reduced, but the feature has enhanced because we are taking the maximum value. So the feature has enhanced. And again it passes through another convolutional layer, and it passes through an activation function, and this is continued. This is a one, two, three layer convolutional, four layer convolutional neural network. So there are at least during image processing competitions or biggest image processing algorithm, there were 19 layer convolutional neural network or a 16 layer convolutional neural networks. were used, and there are available also like some trained models online like UGG's 1916 or something, like AlexNet, GoogleNet, GNet. So these are like 16 layer, 20 layer, you know, neural network, convolutional neural networks that are trained. So what is happening here is, yeah. So what is happening here is we are finally what we need to do is we need to set weight on all these connections. I hope you are able to see some connections here. Again, zoom. So there are different connections that you can see, from this particular image to, these everything. Like, here it is espresso. We have taken as input. That is why it is connecting to espresso. So there will be like lot of connections that is going on, and each connection carries a particular value on the particular, value on that connection. So that is called weight. So finally, what we are trying to teach the model is to adjust the weight, so that the model will predict the correct output. So we'll intuitively try to understand how it is done. So how it is done is, so first we give the espresso image as the input. For example, we have red channel, green channel, and blue channel. That is what is written. Maybe it is not so easy to read, but yeah. So we have three channels and we feed individual pixels and we do convolution and all these things, and we go here. And with all these connections, it reaches, maybe it reaches here. These connections are connected to, this is called a lens layer. It is connected to everything. Like whatever is coming from each of these output, last output diagram is connected to every level. So when we are doing the learning, what it does is, see here, see all these values are reaching espresso. So these are the correct values. So what we do is we assign, see, initially there is some random weights assigned on each of these connections. Then what we do is when we reach through all these connections, finally we reach here. When we reach here, we assign, we increase the weight. So we increase the weight, that is called as reward. So we increase the rate, and when it reaches the wrong answer, we reduces the weight. So this connection previously had a weight, now it is reduced. And here, this connection had some weight that is increased, and that is propagated backwards. So it has some, more to it, like, kind of concept like back propagation in neural network. So that same principle is used here. So that is propagated back, and this is repeated multiple times until the loss function is reduced. And finally, we get a huge matrix of weight. And that huge matrix is called R model. So model is nothing but a huge matrices of weight. And with that weight, what it does is when you give image as an input. So image is nothing but a large pixel, lot of pixels. When you give those pixels, because of the weight, it knows which connection gives the correct output. So one connection only will have, you know, higher value. That is, it is all probability. It is a value between 0 and 1. See, these connection weight, if you add everything, when we give a picture of espresso, the one which reaches a lifeboat will have a probability. When we add all the weights together, it will have somewhere around like maybe 0.01 or something. And which reaches espresso will have zero point 0.9 maybe, 0.99 maybe. So in this case, it will predict that this picture is an espresso with lot of certainty. Hmm. So this training is done on like hundreds and thousands of images of espresso alone. So when since this learns these patterns at different layers, if you give an image which was not in the data set, a new image when it is given, based on the patterns it learned and based on the learned patterns are stored as these weights here. Because of the weight, it will be able to identify the new picture is a espresso. So that is the concept. I know it may not be very clear, but yeah, due to time constraint, we will go to the next topic. But go through this material as well. I'll share this link, and there are a lot of other materials available online where you can refer. Oh, my Teams is stuck. Anyway, I will share the material. That time you can check this. So coming back to our presentation, we have to cover a few things. Presently. Yeah. So since this is again in one dimension, what is happening is, we will be doing this operation in one dimension. So we will have a large single dimension instead of a picture like two dimension. We will have a large single dimension. In the above example, we saw it is 20,000 samples. Sample length is 20,000. So that data is put as a single dimensional input. So that goes through different layers. One is the input signal, then convolutional layers. So again, here we will have a single dimensional filter. So we will have, okay. So we will have a large pixel like this. We will have, 20,000. On that, we will place another filter and we will slide it and do the convolution. Yeah. Then we do the max pooling. So when we do max pooling, again, we said what we do is we have, the convoluted in output. We will have the convoluted output. And upon that, we will place maybe like a 2 by 2 matrix. We add the value, maintain only one value, maintain only one value in the output. That is a maximum of these two. Again, we will do that for the next two, these two, and we will keep another value. Like that, it will get dimensionality reduction, reduces the dimensionality while preserving the key features. That is the idea. Then we do the classification. Then how, yeah, this is how one dimensional convolutional neural layer works. So yeah, this is something similar to what we already explained, like how it learns the features, how the feature get enhanced, how the window slides across the entire signal. They capture different snapshot of the data. That is what we already saw through the image example. So, and I have included one video for one-dimensional convolutional neural network also, so that you can, the slide you can click and you will get this. Then again, what is max pooling? That we already explained what is max pooling, so I'll not spend much time. This is again like, we slide a window and select the maximum value and give it as output. So this is again a dimensionality reduced information where the actual data is, the feature is preserved. And another thing we didn't discuss is flatten and dense layer. So that is the last two operation that we do. So finally, what we get is like, we will send, see, while learning, we will be sending like multiple data. So we will be sending like multiple sets of data like this, like, multiple layers. So, first 20,000 sample, second 20,000 sample, and all these with the labels, like, this particular thing is a good data, this is a bad data, like whatever, we will be sending it to them. And based on that, it will be learning. Finally, what we do is we flatten all these things. We flatten, like, we will put the second value on the, side of this, and we flatten it and send it as a large data. So this is flatten. So we flatten everything into a straight line and then we send it. Dense is nothing but, the final layer. What will happen is every pixel, like every output, whatever output layer, whatever value was there, everything will be connected to the label. Like, all the connections will be made to the output. That we saw in the last one. Like in the last layer, the connections are 100%. Maybe here it is espresso written and here this is cup, or like, different pixels after all the operation we got. And here it is school bus. So whatever it is, it will be connected to everything. Everything that is available in the output data set. So that is dense layer. So there is another video I have included here about dense layer. Then we will do one, small practical example as well. So this is about convolutional neural network. So we will try to, it's a very, very reduced sample, very, very simple example to understand how the operation happens. So here what we do is like we try to prepare the data. We try to normalize the data, extract the features and create a model. Here we are creating a digital twin, and then we are evaluating we try to teach the model to be to identify anomalies. Then we evaluate the performance. So here, the actual application of the machine, which we were telling, it will have four different features to be identified: vibration and I don't know where it is. I think it is not mentioned. Okay. There are different things that is identifying. Here we are only identifying whether the vibration is normal or not. So I will go to this. So you can also use this. This is my GitHub link. So you can click on this and go to my GitHub. And one thing you need is you need a Colab account that is free to use. Colab, maybe many people have. If you don't have, create a Colab account. That is Google, you know, server-based application where you can do programming. So you don't have to create all the dependencies, all the underlying tools. You don't need to install in your laptop. Instead, you can use Google's computers or servers to do your operation. So you can click on this link and you can open Colab. And what you need to do is you have to create a Colab account and you save this in your drive. You can save a copy in your drive. Then, you know, in your drive, you will have a file like this. So to create a Google Colab, it is so easy. It's very intuitive. You can just go and try. Then advantage of using this is, see, for doing deep learning, or if you are interested in learning deep learning, one thing that is needed is we need to have a GPU for parallel processing. For convolutional neural network and all, you can do it. This level of operations you can do without GPU as well. In your normal computer, you can do. But otherwise, we will be needing a GPU. So here, if you see, this is free version of Colab. You can do unlimited operation parallelly, only one or two, but you can do any number of computations, any number of Colab pages you can create, and you can do the programming. So here you will get a high performance CPU, and we will have a GPU as well. So this is a GPU, not a very high performing GPU, but good for most of the operation. So this is like very high performance GPU, but it comes only with the paid version. So this is the GPU that I get now as free. So the RAM of the system is, the server system is 12.7 GB. GPU RAM is 15 GB. Disk size is 112. This varies actually, but yeah, this is what we get for free. And we perform all these operations in that particular server. And when we close this, it will be removed from that. But anytime we can redo the operation. And the downloading of these dependencies and performance of task, everything will be fast because that is connected to the internet. You see, maybe like some of the package when we download it, maybe like 4 GB, 5 GB and all, but still it won't take much time to download that. So here what we are trying to do is we are trying to create a one-dimensional neural network. So we are creating a digital twin, and we are training the digital twin and trying to make a prediction based on a new data. So we will train we will create a model, build a digital twin here. We will build it. We will train the digital twin. Then we will, okay, we will train it here. Then we will make a prediction. We will give a new signal to the model, and the model will tell this is a normal signal or a wrong signal. So I'll go a little faster. I need to stop exactly at 3. So this is the dependencies that we need. So dependency is, one is NumPy. NumPy is again, like if you are doing in your laptop, you have to install all these things. So here NumPy is numerical operation. So it's Python package for numerical operations and matrix multiplication and all. So here again, like as we discussed, it will be like a lot of matrix operations that is happening. Then TensorFlow is a package used for tensor operation or parallel processing, parallel computing. That is also a package, or okay, package we will say. So package by Google. So that is used for deep learning. And Keras is another application layer over the TensorFlow. So this brings in a lot of functionality so that we don't have to sit and program at tensor level or like matrix level. We don't have to view. If you use the command here, it will it will make the programming easy. So here we are importing sequential. So see, this function calls the sequential operation. So we will see why we need sequential operation. Then another layer we need to import, which have the command for convolutional one dimensional convolutional operation, max pooling one layer or one dimensional, and flatten and dense. So these functions also we import. And one more thing is, if you are not understanding what I'm saying now, also you can. This is new feature. Maybe it was available from some time. Yeah, but yeah. So this is one feature that it gives for free. So it uses Gemini AI tool, large language model, to explain the code. If you click on this, you will get the explanation of the code, what this code does in detail. Individual line by line, you will get the explanation. So it is thinking and giving the answer. It will analyze this and gives the answer. So you can read this and understand. And even if you don't have time, or you just need a summary, you can get it from here. So I will run this. Authored by Google. This notebook was not okay. Okay, I will go to my uh, now I have opened in GitHub. That's why this is coming. If it is opened in my Python, in my Colab, okay, yeah, it's okay. I will run it here only. So now I am running in GitHub, but it's okay. So yeah, now what it does is it imports makes the platform ready. These are the dependencies that we need to run the program. It has nothing to do with the program. So now, first we need a lot of signal. So we need the collected data. So what companies does is it collects data from multiple, engine sensors and all those things, and use that particular data to train a digital twin. So since we don't have such data, we create data. So we are creating some vibration data. So here I'm creating a random signal with the middle value at zero point 0.5 and standard deviation as 0.1. So it creates just a random value, but it will be the locus will be towards zero point 0.5. And the median standard deviation will be 0.5, but it can have values like 0.1, 0.2 also. Then the size is it will create 500 samples, each sample having 100 signals. So remember, we are creating 500 samples. So in industry, what they may be having thousands or hundreds of thousands of samples, and each sample may have 20,000, 30,000 signals. So it's data points, data points. So here we are having 500 samples, and each sample having 100 data points. So vibration is centered around 0.5. Here the vibration, like we call it vibration data because we are working on vibration now. So we create a random signal which has vibration centered around 0.5. That we consider as normal vibration. Then we have faulty data. So here another thing what we are doing is we are creating a label. Similar dimensional, we are creating a matrix with zero value. So if you print this, you will see maybe print. Okay, everything I'll print. We'll see the dimension here. Okay. Normal labels, normal data. Oh, okay, sorry, I didn't run this. Okay. Okay, we need to run this first, otherwise it didn't know they can about this. Okay. So I ran this. Now see, this is like 500, 100. That is the expected one, right? Normal data, 500, 100. And this is a 500, by 1, 500 by 1 matrix with all zero mentioned in it. That is for labeling. So we mentioned this data set with a value 0. So for example, consider 0 is equal to normal. So if the value 0 is given to attach to this signal, that means this particular sample, or this 100 value attached to 0 means it is a normal signal. So in the next case, we will perform the same operation. This time the vibration is centered around 0.8. And here we create a label called 1. Here a 500 dimensional matrix is created with 1 in it. So we will finally attach that 1 at the end of all these data. Then 1 means faulty signal. So we are trying to learn. So this is supervised learning. This is a labeled data set. So what we are creating here is labeled data set. So here we have the data and here we have the data, sorry, label. So this label for normal is 0, label for faulty is 1. Then what we do is we concatenate, we bring, yeah, we attach the normal one and the faulty one. So, the dimension of this will become big. So we can see the dimension as well. So if you see here, we concatenated. So the dimension of the matrix become 1000. So the first 500 signal will be normal and the next 500 will be faulty. So we concatenated and we created a 1000 by 100 matrix. Hope this is clear. And Y shape also is concatenated. That is like now we will have first 500 values as 0 and next 500 values as 1. Now what we do is we shuffle the data. So shuffling is done to reduce the bias. So if we don't shuffle and try for give it for learning, what it happens is the first 500 values will be normal value and next to 500 value will be faulty value. So when it tries to adjust the it won't be able to learn properly because it is learning all the good values first, then all the bad values next. So the learning will be biased and the output won't be good. That is why we are going to shuffle. So here what we are going to do is, we will create an index. So what we are creating is we are creating a new array called so here what we are creating an index like 1 to 1000. Consider like 1 2 3 4 till 1000. Not it. Okay. See, we are having an index created from 1 to 1000. So consider it as 1 2 3 4 till 1000. Then what we do is we shuffle the numbers. So maybe 1, after 1 it may be 888 or like 750. Then it goes on till like shuffled manner. So we shuffled that number, shuffled the indices, and then we attach the shuffled value to X and Y. X is our data point, Y is our label. So the same index get attached to the the data points and to the label. So if it is a first data is a normal one. So that will get one index attached to it. So maybe it is 800. Let us call it the value 800 is attached. The corresponding Y value or the label value also will get 800. So now we know the 800th value is it got shuffled. Just think it got shuffled. So now we shuffled the data. So the normal data and abnormal data or the faulty data got shuffled in between along with the label. So label is also along with it, shuffled along with it. So now what we are going to do is, so if you are not understanding, you can go and read this and understand. Due to time constraint, I am going a little fast. Then what we do is, yeah, now we are calling the sequential function. So see, the sequential function, is used for linear operation. Yeah, here you can read by clicking itself, it is giving some, information about it. So this is for sequential operation, and convolutional 1D is a sequential operation. So this you can see here, we are defining a filter with the size 16 and 16 filters. Okay, this is not filter size. So here we are calling 16 different filters. So 16 different filters will do convolution. So each filters will have different weights in that filter. So why we need multiple filters is to enhance different features or like learn different types of features. Some may be learning like some kind of noise, some may be learning some level of vibration, some may be learning vibration due to a specific failure. So 16 different filters are considered, and the kernel size, the size of the filter is 3, and the activation function is ReLU, and input shape is 100. That means like we are kind of see, yeah, already it is 100. Yes, so input shape is 100. We know the sample size is 100. So I'll run this. Now what we do is we are doing the max pooling. with a size of 2. So again, max pooling we explained, it will have a filter of size 2, and it adds and it checks and keeps the maximum value and discards the lesser value. And another one is we are again doing the convolution with 32 filters this time with kernel size 3 and activation ReLU and max pool. Again, we are doing another max pool. Then we flatten the model. We flatten. This is the function for flattening. Then we dense. Dense means we will have a complete connection to the output. We do a dense operation. So, this part to understand completely or to appreciate this completely, you need a, understanding on the neural network. Some people may already know. So I was also, when I was teaching, I was taking neural network in semester 8. So I know that, very well. So if you know neural network, those who knows neural network very well, they will understand like most of the operation like filter, kernel, activation, max pooling, dense, flatten, everything. Yeah. Then what we are going to do is we are going to train the model. Now we created the model structure. Now we are going to create the model. This now, it is packaged as a model. We are telling what it does, it needs to do. So this model should, now we created a structure of model and we are telling what is the operation of the model. It should optimize for accuracy and reduce the loss. That is the functionality or the some equation that we are giving to the model. So here this model is a huge matrix, and this matrix operation what it is performing is like, this matrix will be part of a large equation, and that equation is, coming from this particular command. You can read about it. So it what that, matrix or like this model is trying to do is it is trying to optimize. The optimizer uses adaptive movement, like I forgot the name, adaptive movement based optimizer or something. So there are multiple optimizers. So this optimizer is faster and, takes only lesser number of iterations. So that is the advantage of Adam optimizer. And this is the loss function used. Loss function can be like multiple, you might be already knowing, like, see, this is the function what we are trying to reduce. We are trying to reduce the value of this loss function. And finally, what we are trying to achieve is accuracy. Now we are going to train the model. So now we have input and a label. So we know the input and we know the label. Label is normal signal or faulty signal. So now what we do is we have this command fit. So fit command is used to train the model. So now what we are doing is we are giving the information, the data sample, and we are giving the label. We give the input and the label to it. So this is a supervised learning that is going to perform. We are telling this signal is this signal, this label. This signal is attached to this label. So we are doing the run for 10 times. So, epoch means one epoch means how, one epoch means the model will go through all the data points. Here we have 1000 into 100 data points. So it will go through all the data points. So it will 10 means it goes through the data points 10 times. So that is needed to train and retrain to make it better. Batch size means 32. Each time it will pass 32 samples. It will be split into 32. Then, it will be, each time 32 sample will be passed. So in the first layer, there will be like 32 different input layer we can consider. Then validation split is 0.2. Here, what does it mean is like, 80% of the data will be used for training and 20% for validation. So at each epoch, it will use 80% of the data to train the weights or adjust the weight. It does back propagation to adjust the weight, and rest of the 20% is used to check whether the value is correct. Because since it is labeled, we can do the checking whether the identification, what it does, like, this data is normal, this data is faulty, whether it is telling correctly. If it is not correctly, again, it will, try to increase the, optimize the output. So now we run this. Now we can see it is, first epoch is running and it gives an accuracy. See, it's only 0.4, 0.5, loss is 0.6, then validation accuracy, validation loss. So yeah, this is how, by third, fourth iteration, we got an accuracy, very high accuracy, but still validation loss is 0.15. That means like validation loss means See, sometimes there could be some level of error happening, but how large is the error? Like, mm, how much far is from the optimized value? So such kind of a parameter. Then in multiple run, when we ran the 10th, we see the validation loss also has reduced. So now if you see all the values have come to a very good, you know, optimized value. So now this model is a digital twin. Now this model, whatever input we give, the model will be able to understand what is that input, and it will tell us what is that, what is the output, what to expect from that signal, what it understood from the signal. So here we are creating a new sample. So it is again no, random signal, okay, no, with a sample with moderate vibration. We keep zero 0.6 and 1 with 100 size. There's only one sample is needed. And we feed it to the model. We created a model above and we use that model to make the prediction. Mm. And we will, so the model, what it does is based on the value it gets, it makes a probability prediction. So it will make a value, it gave a value 0.135. And the prediction is like if it is less than, see, our value is zero. If it is zero, it's only two sample. That is why, like, it's easy. So if it is zero, it is uh, normal value. If it is one, it is normal. So this made a prediction saying it is 0.135. So it is towards normal. So it will give, prediction as normal. So this is creating a probability. Probability saying, I think it is more towards normal. Sometimes, or it can make up if we increase this value. For example, I'll give it as 0.8, zero 0.9 or something. Then it will make a prediction which is like zero 0.9. So now it is kind of certain, and almost 100% certain that it is a faulty signal. So you can see the prediction made is faulty. So this is a example of a one-dimensional convolutional neural network. Ooh, the time has passed as well. Okay, yeah, I will go back to my presentation and see, you can go through this and you can click on this link and make a copy of this in your Google Colab, and you can create an account and try this thing, understand this thing, and you can have some other examples as well. So yeah, that is what majorly I will discuss. So there is a lot of computational, tools and infrastructure needed for it. This is another application which we will not discuss. You can go through it. So here you can see what are the, XGBoost is used, another deep learning or like machine learning algorithm. So if you know this algorithm, you can explore those as well. Yeah, I'll not go into that. Then these are some challenges and how we can improve and what are the future trends. There are like collaborative training done between OEMs, different kind car manufacturers, and there can be quantum machine learning. That is something that is in research now. Then digital twin ecosystems, cross system, like multiple system or like multiple integration between multiple model engine and battery, or like engine and or battery and maybe a, HVAC system combined. It can make better results, better collaboration, such things. So yeah, that is conclusion. Yeah. Okay, I will stop with this. But yeah, if you are interested, I would request you to go through this slide and try to understand more. And you can message me as well if you have any doubts, if you are interested to know something in detail about what I have explained, especially about the convolutional neural network or the collab part. You can message me and I will be able to help. Yeah, with this, I'll conclude my session. Yeah.
So dear participants, if you are having any doubt, you can unmute your mic and ask.
Yes, yes, please.
Okay, sir. Thank you very much, sir. Thank you
Okay,
very
okay.
much for your
Yeah.
intuitive thought. So now a small vote of thanks. So on behalf of the organizers and participants, I extend my heartfelt gratitude to Dr. Akhil Jose for delivering such an insightful and engaging session. Your expertise in autonomous vehicle technologies has provided us with a deep understanding of cutting-edge advancements in the automotive industry. The detailed explanation you gave about this convolutional neural network and the various online sources you provided is very helpful to us. We sincerely appreciate the time and effort you took to share your valuable insights with us today. Your session has undoubtedly broadened our perspective and will serve as a foundation for future explorations in this domain. Once again, thank you, sir, for being with us today and sharing your expertise. We hope to have more opportunities to interact and learn from you in the future. Thank you very much, sir. Thank you. Thank you for being with
Okay.
us.
Thank you.
Thank you,
Thank you
sir.
for the operation. Thank you for the opportunity and thank you for listening to me. Yeah. Okay. Have a
Okay.
nice evening. Yeah. Bye.
Okay. Thank you, sir. Thank you.
Yeah.
Bye.
Thank you. Thank you so much. Bye.
Thank you, sir. Thank you. So, dear participants, our next expert is also with us now. Sir, good evening, sir.
Good evening, madam. My screen is visible, ma'am.
Sir, no, wait, sir. Yes, sir. Yes, sir. It's visible. Yes, sir.
Okay, madam. Okay, ma'am.
Okay, sir. So, good evening, everyone. We are entering into our second session. So, it's an absolute honor to introduce our distinguished speaker, Dr. S.Senthil Kumar, a distinguished professor in the Department of Electrical and Electronics Engineering at the prestigious National Institute of Technology, Tiruchirappalli. With over 23 years of experience in academia and research, Dr. S.Senthil Kumar has made remarkable contributions in the field of electrical machine drives, hybrid electric energy conversion systems, power quality, and renewable energy systems. Dr. S.Senthil Kumar earned his BE in Electrical and Electronics Engineering from Tyagaraja College of Engineering under Madurai Kamaraj University, followed by an M.Tech in Electrical Drives and Control from Pondicherry Engineering College, affiliated with Pondicherry University. He further pursued a PhD in Electrical and Electronics Engineering at NIT Tiruchirappalli. He has got over 23 years of teaching experience. He has been a part of NIT Tiruchirappalli since 2006, progressing from assistant professor to associate professor and currently serving as a professor since March 2024. His research interests include electric machine drives, hybrid electric energy conversion systems, energy conservation, microgrids, power quality, power electronic interfaces for renewable energy systems, and the development of analog and digital controllers for power converters. He has contributed to numerous refereed international journals and has been instrumental in several sponsored projects, such as the design and development of a solar photovoltaic powered cold storage system and the development of a renewable energy laboratory. He has served on various academic and professional committees across multiple institutions. His extensive research in power electronic interfaces for renewable energy and microgrids, along with his leadership in sponsored projects such as the development of a solar photovoltaic powered cold storage system and renewable energy laboratories, highlights his commitment to innovation and sustainability. We are truly privileged to have Dr. S.Senthil Kumar with us today, and we eagerly look forward to his insightful talk. Sir, it's an honor to welcome you. Welcome you, sir.
Thank you, ma'am. Thank you for your introduction. Can you hear me? Hear your voice?
Yes, sir. Yes, sir. We can hear you.
Yes, ma'am. Thank you, ma'am. Thank you for your introduction. Very good evening to all of you. Today, my talk is related to how the AI techniques we were using for the smart grid system. So, in this regard, first we need to understand what is smart grid. See, here you see that this image represents the interconnecting of various things like a distributed generation, load, so everything is there. So the smart grid is an electricity network based on digital technology that is used to supply electricity to consumers via two-way digital communication. So this is the definition which is given in all the textbooks. So this system allows for monitoring, analysis, control, communication within the supply chain to help improve efficiency, reduce the energy consumption and cost, and maximize the transparency and the reliability of the supply chain. So coming to the smart grid definition by National Institute of Standards and Technology, NIST. A modernized grid that enables bidirectional flows of energy and uses a two-way communication and control capabilities that will lead to an array of new functionalities and capabilities. So according to the IEEE, smart grid system is a large-scale system where each functional domain consists of three layers: the power and energy layer, the communication layer, and the IT or computer layer. The layer 2 and 3 are enabling the infrastructure that makes the existing power and energy infrastructure smarter. I hope you can understand what is the meaning of smart grid. So coming to the smart grid, the need for smart grid. The need for smart grid arises from the increasing complexity and the demand of modern power systems. A smart grid is an advanced electricity network that uses digital technology to monitor, manage, and optimize the generation, distribution, and the consumption of electricity. Below are the key drivers for its adaptation. So rising energy demand, that is a global growth in energy use, necessitates efficient electricity distribution systems. Traditional grids offer struggle to handle peak loads, leading to outages and inefficiencies. So integration of renewable energy sources, renewables like solar and wind are intermittent and unpredictable. A smart grid enables real-time balancing and integration of these sources, ensuring the reliability. So coming to the grid monitoring and aging infrastructure. So existing grids in many regions are outdated or prone to failures. Smart grid provides an opportunity to upgrade infrastructure with advanced monitoring and control capabilities, enhancing reliability and outages, reducing outages. The smart grids quickly detect faults and isolate them, minimizing downtime. Advanced analytics predicts potential failures, allowing proactive maintenance. Energy efficiency and cost savings. So like enables a demand side management by providing consumers with the real-time data on usage. So reduces the transmission and the distribution losses through optimized operations. So coming to the electrification and the decarbonization goals, support electric vehicles and distributed energy sources, facilitates the transition to a low carbon economy by enabling smarter, cleaner energy use. So coming to the cyber security and grid resilience, like enhanced cyber security measures in smart grids to protect against physical and cyber threats, resilience against natural disasters and other disruptions is improved through decentralized and adaptive systems. So coming to the smart grid drivers, so it is with respect to the various indexing like growing energy demand, economical growth, policy and regulation, technology advancement. It covers with infra reliability and security, energy independence security, like GHG reduction. So climate changes, increasing renewable energy generation, political like that. It is connected with various terms. So energy transition and sustainable goals that integrates of renewable energy, like facilitates the efficient incorporation of solar, wind, and other renewable sources into the grid. Decarbonization supports a global efforts to reduce greenhouse gas emission by optimizing energy use and promoting clean energy sources. So coming to the renewable energy integration, the push for cleaner energy resources like wind, solar, and hydro necessitate grid that can integrate these intermittent energy sources. Smart grids ensure real-time balancing of generation and consumption. So coming to the growing electricity demand, increased resilience on electricity due to urbanization, industrial growth, and electrification of sectors such as transport, and example is the EVs. Need for a system that can handle higher loads with the flexibility and reliability. So coming to the functions, it involves with various functions. So for example, the power quality and optimize the assets, enables the electricity market, accommodate a generation operation, and resist attack, consumer participation, self-healing, enabling high penetration of intermittent generation sources. So the opportunities are smart grid are energy demand and demand management. So particularly the load balancing. The smart grid enables dynamic load management, reducing peak demand and improving the grid stability. Then demand side response, consumers can adjust usage based on real-time pricing or incentives leading to energy savings and cost reduction. Energy loss reduction, advanced monitoring system reduce transmission and distribution losses. Consumer engagement and empowerment, like smart meters, provide detailed insights into energy usage, enabling better management by consumers. Home energy management systems allow household to optimize energy use through automation and scheduling. Coming to the incentive programs, so like promote energy efficient behavior with rewards or dynamic. So the economic growth and innovation refers to job creation, opportunities in R&D, manufacturing, installation, and maintenance of the smart grid technologies. New business models, for example, supports the growth of energy as a service models and peer-to-peer energy trading. Startup and entrepreneurship encourages innovation in energy technologies and software solutions. Environmental benefits like a carbon footprint reduction, sustainable urban development like that, and advanced data analytics and AI applications. So I just want to cover this topic. And predictive maintenance, energy forecasting, and cybersecurity enhancements. For that, we are using effectively the AI. So the AI to predict the equipment failures before they occur. So for improving the grid planning and the efficiency with accurate demand and supply predictions, and AI-driven tool to detect and prevent cyber threats in real time. So coming to the electric vehicle integration, like vehicle to grid, grid to vehicle like that. So vehicle to grid, the use of EV as a mobile energy storage unit and charging infrastructure optimization, ensure reliable power supply for EV charging networks, dynamic load management, manage the impact of EVs on the grid, then policy and regulatory opportunities, incentives for adaptation. Governments can promote a smart grid adaptation through subsidies and tax benefits. So standardization, develop a global standards for interoperability and security. Public-private partnership that indicates with a foster collaboration for large scale smart grid deployment. So coming to the challenges. The challenges with the smart grid that indicates with a high initial cost, infrastructure investment, upgrading legacy grid systems and developing smart technologies require significant capital and consumer load. Installation of smart meters and home energy management systems may burden end users financially. Then uncertain ROI, long-term benefits may not be immediately evident. They are deterring stakeholders. So coming to the technology complexities, integration with the legacy systems, then interoperability issues like a lack of standardization among the devices and the platforms can create the complexity, compatibility issues, data overload like managing, storing and analyzing. The vast amount of data generated by smart grid requires the advanced solution. So coming to the cyber security risk. With respect to the cyber security, increased vulnerability, like connecting critical infrastructure to digital network, exposes it to potential attacks. Then data privacy concerns, sensitive consumer data collected by smart meters and device must be protected. Complex threat management, the dynamic nature of the cyber threat demands robust real-time security measures. So coming to the regulatory and the policy barriers, inconsistent policies like a variation in regulation across the regions hamper large-scale deployment. The rate design challenges, balancing utility revenue needs with the consumer affordability is complex. Slow policy adaptation, regulatory frameworks may lag behind the technology advancements. So consumer acceptance and engagement. So awareness gap. Many consumers lack understanding of smart grid benefits, privacy concerns, fear of data misuse can hinder acceptance of smart grids, smart meters and devices. Behavioral resistance, encouraging changes in energy consumption habits is difficult. So coming to the scalability and regional constraints, urban versus rural divide, deployment of smart grid technologies in rural areas may not be economically viable. Then scalability issues, expanding pilot projects to large scale deployments poses significant challenges. Geothermal barriers, cross border energy, trading grid integration face potential and technical hurdles. So the scalability that indicates with urban, as I had told you, then environmental and social concerns are something like e-waste generation, equity issues, aesthetic concerns, economic and market constraints that indicates with revenue models, cost sharing conflicts, then market competition. So the benefits, we can say that enhanced energy efficiency by employing the smart grid concepts. So integration of renewable energy sources, improving the reliability and the resilience, cost saving for utilities and consumers, empowered consumers, environmental benefits, support for electric vehicles. So coming to the difference between the conventional grid and the smart grid. Smart grid is a bidirectional distribution and a conventional grid is a one directional distribution. It is decentralized generation and a conventional is a centralized generation, and consumers are also producers, whereas here the conventional grid passive consumers. Backup in case of emergency, no customer owned storages, sensors to access the stability, minimal use of technology, quick restoration after disruption. Disruption can create domino effects, automated off-peak purchase, electricity rates depend on the demand, possibility for complete independence, strict resilience on the grid, smart meters for energy saving, meters only shows the consumption. So the national initiatives with respect to the smart grid is India Smart Grid Task Force that indicates with the Ministry of Power, Government of India. The another one is the Bureau of Indian Standards. Then the other government entities. Then the international agencies also, and industry, academia, research bodies. And coming to the international initiatives with respect to the smart grid, that indicates with the international smart grid action network. So that indicates with something like WG3, the cost benefit analysis and toolkit, WG5, international research network, and power and T&D systems, then smart grid transitions, flexibility markets. So among this, for creating the smart grid systems with various applications like renewable energy sector, electric vehicle sector, industrial automation sector, consumer electronics sector. So everywhere the power electronics plays a crucial role. So when you are referring with the power electronics, we are expecting with the efficient operation. So efficient energy conversion and conditioning of the electrical power. So now the topic is AI. How the AI it will be helpful for the smart grid system. I have given some introduction earlier. Any doubts you can ask me. So now the challenges that driving the need for AI is increasing in complexity. So first of all, you need to understand with respect to the AI, importance of the AI. So the AI is emerged as a powerful tool for enhancing the performance and the functionality of the various systems. With AI, can achieve improved efficiency, reliability, fault detection, energy management, like that. So the AI algorithm enables the analysis and modeling of the complex system, allowing the identification of the patterns and corrections that are difficult to discern with the traditional methods. So this capability makes AI particularly useful in power electronics systems. So power electronic systems where accurate modeling and control are essential for the optimal performances. So moreover, AI can be used in real-time monitoring and control of the power electronic systems, enabling intelligent decision making and predictive maintenance. So that we need to understand by continuously assessing the system data. The AI algorithms can detect and diagnose fault before they result in the system failure, improving the system uptime and reducing maintenance cost. Additionally, AI can optimize energy management in power electronics drive system, enabling them to operate at peak efficiency levels and reducing energy consumption. So the integration of the AI in electric power systems offers significant advantages, including improved efficiency, reliability, fault detection, energy management, predictive maintenance. So therefore, it is therefore important to explore and develop the potential of the AI in the electric power transmission, generation, transmission, and the distribution system, that is smart grid system. So to maximize the performance and the functionality of the critical systems. So here I have said that the challenges are driving the need for AI is increasing in complexity. So like in power electronic systems are becoming more complex with increasing component count and sophisticated control systems. So need for optimization like efficient optimization, efficient operation, reliability, and fault diagnosis are the crucial but challenging to achieve with the traditional methods. Growing data availability, So the power electronic system generate a very vast amounts of data that can be leveraged for AI solutions. So the AI is the ability of a computer or machine to mimic the human cognitive functions such as learning and problems. So the relevant AI techniques. So the focus on machine learning, deep learning, and neural network, which are particularly relevant to the power electronics. So I can say that they are in the textbooks. The AI definition is AI is a field of computer science that involves the development of algorithms and systems that can perform tasks that would typically require human intelligence. There are several AI techniques, including machine learning, fuzzy logic, and meta-heuristic methods, which can be used for power electronics and drive systems. The machine learning is a subset of AI that involves the development of algorithms that enables computers to learn from data. So without being the complexity, without being explicitly programmed, the machine learning algorithms can identify patterns and correct correlations in data and make predictions or decisions based on this analysis. So this technique can be used for various applications such as control, optimization, um, fault diagnosis, energy management like this. So the another tool for AI, fuzzy logic. Fuzzy logic is when the complexity is more, we can use the fuzzy logic. So that means the fuzzy logic is a mathematical technique that enables the computers to reason about uncertainty and imprecision. It involves representing the data using linguistic variables and applying logical rules to those linguistic variables to make decisions. The fuzzy logic can be used for applications such as control, optimization, fault diagnosis, and energy management like that. The meta-heuristic methods are optimization algorithms that are inspired by natural processes such as evaluation or swarm behavior. These methods are used to solve complex optimization problems where traditional methods are not effective. Okay, so the meta-heuristic methods can be used for applications such as power electronics design and optimization and energy management like this. So here you can see that a few AI applications like robotics, then neural network, machine learning, fuzzy logic, and AI intelligence that connects with these terms. So natural language processing, expert system, it can be applicable to microgrids like for example, life cycle prediction of the battery, life cycle prediction of the PV, scheduling of the load, scheduling of the generation, and forecasting of the wind turbine, I mean the wind power generation, effective power transmission, all those things it is possible with the AI. Like, see, in just we can say that energy management, load and generation, forecasting, fault detection, classification and protection, converter control, cyber attack, detection and cyber security, fault tolerant control, scheduling of generation and storage system, real-time pricing, prediction of electricity like that, demand side management and demand response. So for all these applications, we can use it. In addition, the AI applications to the power electronics and control like that, plant control, the power converter control. So we can apply it for the PID tuning with the AI. So employing the genetic algorithm like a PSO, or we can use it with the fuzzy, or we can use it with the ML. Anything it is possible. So and the another important application is the condition monitoring. So use of AI to analyze sensor data and detect anomalies, providing insights into the health of power electronic components, and employ AI-based security measures to protect the power electronic systems from cyber threats. So the benefits of the AI: efficiency, reliability, fault detection, energy management, predictive maintenance, design. For all these aspects only we were using with AI. So sometimes we need to have the adaptive control. For example, grid connected systems with respect to the renewable energy. For that, we can have the adaptive controls. So for that also we can implement with the AI or natural language processing. So help the devices respond to voice command. Then computer vision AI can help devices respond to virtual inputs. So the AI tools like machine learning, we can use it deep learning, natural language processing, computer vision, expert systems like this. So the comparison I have given here. This comparison very clearly states that how it is useful for the power electronic system. It has own advantages and disadvantages that it is listed here. So for example, the machine learning algorithm. So it is having the ability to learn from data and improve performance over time. Adaptability to changing conditions, can handle large amounts of data. But the disadvantages require a significant amount of high quality data for training, may suffer from overfitting or bias. Black box nature of models can make them difficult to interpret. So the how to access, collect more data to improve model performance, use regularization techniques to prevent overfitting, use models interoperability tools to explain the model behavior. Coming to the fuzzy logic, it is also extendable for applications like a power electronic systems. So ability to handle imprecise or uncertain data, uncertain information provides a framework for representing the human knowledge and expertise can handle non-linear systems. The disadvantage is difficulty in determining the appropriate membership functions and the rules or lack of scalability to complex systems. So how to access in the sense, use domain expertise to inform the design of membership functions and the rules, explore the hybrid approaches with other AI techniques for scalability. So coming to the meta-heuristic methods, like ability to handle the complex optimization problems with the non-linear constraints that can quickly coverage to good solutions can handle multiple objective functions. So lack of guarantees of global optimality may require significant computational resources, sensitivity to parameter settings. So use multiple runs with different parameter settings to improve the probability of finding good solutions, explore hybrid approaches with other optimization techniques for increased robustness, develop customized meta-heuristic algorithms for specific applications. So coming to the AI-based control and optimization with respect to the power electronic systems. So let us consider the applications of the machine learning in power electronics and control optimization. Machine learning has a various applications in power electronics and control optimization. One of the primary application is in the design and the control of power converters. Machine learning algorithms can optimize the control parameters for various types of power converters, such as AC/DC, DC/DC, DC/AC, then AC/AC like that. So the optimization can improve the converter performance in terms of efficiency, response time, and stability. So coming to the another applications of the machine learning in power electronics is the fault detection and diagnosis. Machine learning algorithms can analyze the converter's output waveform and detect any deviations from the expected output. So this analysis can help in diagnosing the fault in uh, converters components and identifying any potential problems that can lead to failures. So also the machine learning can also be used in predicting converter behavior under different operating conditions. The algorithms can learn the converter response to different load and input conditions and predict the converter output for different operating conditions. So this prediction can help in designing the converter for different applications and identifying the optimal operating conditions for the converter. So some of the case studies already executed. I just want to, the several case studies have been demonstrated the effectiveness of the AI based control techniques in power electronic systems. One such case study is the application of the neural network based control in battery charging applications with respect to the DC-DC converter. The neural network was trained using the back propagation algorithm to optimize the converter control parameters. The neural network um, control algorithm was found to be the more efficient and accurate than the traditional control algorithm. So the another case study is the application of fuzzy logic based control in grid connected renewable energy systems. So the fuzzy logic controller was used to regulate the output voltage of the PV system under varying input conditions. The fuzzy logic controller was found to be more effective in regulating the output voltage than the traditional control algorithm. So coming to the challenges and the limitations using the AI in power electronic systems. So although the AI based control systems offer several benefits for power electronics control, they are also pose several challenges and limitations. One of the significant challenges is the complexity of the algorithms and the lack of transparency. In the decision making process, it can be challenging to understand how the algorithm make the decision. So which can make it difficult to diagnose and correct any problems that may arise. The another limitation is the AI-based control is the need for large amount of data for training the algorithms. The data used for training the algorithms must be representative of the real world operating condition of the converter. So obtaining the data can be the time consuming and expensive. So we can see that the various AI tools, the machine learning algorithms, like ANN, the support vector machines, decision trees, genetic algorithms, particle swarm optimization, like that. So the applications like modeling and control of the power converters, like we can use support vector machines. In fact, we were used for fault diagnosis in the PV systems. So PV panels and decision trees is also used for fault diagnosis and prognosis, and optimal design and parameter tuning of the power electronic systems. So PSO, which is used for optimal power management and control in renewable energy systems, which is used to optimize the power output of the renewable energy sources and the control of the power electronic devices for maximize the efficiencies. So one can understand the AI-driven fault diagnosis and prognosis in power electronics. So the applications of AI is a diagnosis and prognosis. The AI-based techniques have been widely used in power electronic systems for fault diagnosis and prognosis. These techniques can help to detect faults early in early and predict their failure behavior, which can improve the system reliability and reduce the downtime. So some of the applications of the AI for fault diagnosis and prognosis in power electronic systems are as follows. One of that, fault detection in power electronic converter, fault detection in power electronic devices such as IGBT, MOSFETs, prognosis of the power electronics components such as capacitors and inductors, fault detection in electric machines such as motors and generators, prognosis of bearings and other mechanical components in electric machines. So the techniques for detecting and predicting the fault is, I said that one is the support vector machines, which is used for detecting the fault in IGBTs and MOSFET. Then ANN, which is used for fault detection in electric machines like a motor or generator. The fuzzy logic is also which is used for uh, detecting the fault diagnosis in IGBTs and MOSFET. Expert system is also used for the fault diagnosis in power electronics. So some of the real world examples of the AI based diagnosis and prognosis in power electronics. So the fault diagnosis in the wind turbine. So here in the study, the ANN based fault diagnosis system was developed by the wind turbine for the wind turbine. The system was able to detect a fault in the turbine's gearbox and predict the remaining useful life of the gearbox. The second one is the fault diagnosis of the induction motor. An SVM based fault diagnosis system was developed for induction motor. The system was able to detect the faults in the motor and classify them into the different fault categories. So prognosis of the capacitors in a power electronic converters, that indicates with a fuzzy logic based system was developed for prognosis of capacitors in power electronic converters. The system was able to predict the remaining useful life of the capacitors. So this table explains you the AI-based diagnosis and prognosis technique, and with respect to different techniques, how it will be useful for the fault diagnosis. So this table summarizes the techniques vary in their accuracy, complexity, sustainability, and suitability for different types of loads. I mean the faults. So this table is also useful for references for the researchers and the practitioners looking into implement AI-based fault diagnosis and prognosis in power electronic systems. So these are the various models. And here you can see that the applications of meta-heuristic methods, either it may be the population-based method or trajectory-based method. So which one offers the superior performance, particularly the design, control, maintenance like that. So the trajectory-based method, it will provide the superior performance in design and control. So the maintenance, the conventional genetic algorithm itself, it is sufficient. And this is what the supervisory learning methods is also there, like with respect to the neural network, conventional neural network, NN with the fuzzy logic, NN with the recurrent unit, and NN with the conventional structure. Each has its own advantages and limitations. So depends upon the applications where we need to use, which technique we can use, that we can choose it. So similarly, the unsupervised learning method and applications to power electronics is clustering and data compression. So that also having some of the advantages and the disadvantages. How we can use, where we can use, that we should be see that. So with respect to this diagram, I have taken from one of the review paper in IEEE. So the usage statistics of the machine learning methods in power electronic systems. So like most of the places it is used for supervised learning only. Few only they are using with unsupervised learning. So this is what the flowchart maintenance in power electronic systems with respect to condition monitoring and health assessment. For example, the power electronics and the converters systems, system parameter identification, data processing, future mining, anomaly detection, fault diagnosis, and remaining useful life prediction (RUL). So for that decision making, wherever the decision making we require, optimum by maintenance decision, control policy adjustment, power routing. So for this we are using with training the database. So historical degradation and failure data, failure mode and effects of analysis, and accelerated training experiment. So for that we need to have the offline models also. So the advantages and the limitations of AI algorithms in control applications, one can see that how it will be useful, and that information it is given here. And coming to the energy management, uh, so repeatedly how this one, I mean the AI, which is useful for the energy management applications. Uh, the role of AI in optimizing the energy management in power electronic systems. So it requires the energy efficient management. So the energy consumption of this system as a function of various factors. Here you see that the conventional generation is also there, the non-conventional generation is also there, the renewable power generation is also there, how you are scheduling the load. So for that reason, we can use the AI. The energy consumption of this system is a function of various factors that, such as load demand, external environmental conditions, system topology, control parameters. The use of AI techniques in energy management can help optimize energy consumption, reduce energy cost, and increase the reliability of the system. So the AI techniques such as the machine learning, neural network, or fuzzy logic can be used to develop models that can predict energy consumption based on the historical data and the external factors. So these models can then be used to optimize the energy consumption by adjusting the control parameters such as switching frequency, modulation index, and duty cycle like that. So the applications of the AI for energy forecasting and load scheduling, demand side management that it is indicated, and uh, the artificial intelligence has been increasingly used in power electronic design. So including the areas of optimal sizing, layout, and topology selection. So the AI which is used for efficient and effective power electronic systems. So the AI is used for optimal sizing, and the include the I mean this the tools we can use like a genetic algorithm, PSO, ANN, like that we can use it. So and few developers, um, I mean already they developed some uh, solutions, power design technologies. So they developed some solutions for power electronic circuits. Then XOPT foil, Exoptics, they developed one AI-based algorithm optimizing the power electronic designs and topologies. So Infineon Technologies, they developed optimization tool for power MOSFETs. So then auto DC, this we are using effectively for uh, battery charging applications, and new power AI-based platform for optimized the design and the control of power electronic systems. So I just want to I have briefed about the AI. So coming to the smart grid technologies. So the elements of the smart grid technologies that indicates with substation, that indicates with the monitoring control. So system monitoring, voltage and like that. So then advanced metering, market support, distribution automation, the applications like distribution management system, outage management system, communications like that, all are included. A smart substations. A smart substation is a digital substation that uses the advanced technology to monitor, control, manage electrical assets. So smart substations are the key component of the smart grids, which are designed to provide a safe, reliable, and efficient distribution of the electricity to consumers. So substation automation also we were using with that also come under the smart grid only. Then smart grid functions, the substation automation integrates with smart grid functions like a demand side response, distributed energy resource management, and a predictive maintenance like that. Then the advanced metering infrastructures like a digital meters and instrument transformers provide data for usage settlement and innovative rates. Distributed energy resources substation systems control and integrate local renewables, storage and microgrids. The facts like a substation control can quickly adjust the power flows to relieve cognition and dynamic line rating. That also it is there. Then wide area monitoring control, time synchronization, user access management, then communication networks. So all these things we were brought it with respect to the smart grid concepts. So like feeder automation, then improved customer service, reduced downtime, real-time information, reduced capital investments. For all these things, we can bring it with the AI also. AI assisted with the smart grid system. So this is what the energy management systems in a smart grid. So you can see that this is what the microgrid system that contains renewable energy sources, battery, load, or diesel engine, electric vehicle, the electrical grid, how it will be connected. So how the way in which we are monitoring, how the way in which the energy we are managing, how we are scheduling the load. For that we can use it with AI. Then we can use it with the AI. Along with the AI, we can bring it with the smart grid concepts. So the energy management system in a smart grid system manages and optimizes the energy generation, storage, and the consumption of the electricity to ensure the reliable and safe power supply. So the balance supply and the demand, the energy management system maintains the balance between the supply and demand of electricity, reduced cost. So that is EMS reduce the cost of power generation and energy bills, improved sustainability, improved reliability, improved safety, share energy. So that means the EMS shares or exchanges the energy between the two energy resources, store excess energy, balanced load, monitor in real time. So the facts in smart grid like SCADA, phasor measurement units, so advanced actuators, substation automation we were using, distribution and automation also we were using with the smart grid concepts. Then customers like advanced metering, demand side response, and the distributor resources, those places we were using. Like the facts, it will be parallel with the transmission lines to control the current and the series and in series to control the voltage. The benefits is increase the power transfer capability of the lines and change power flow over specific routines. They can also help maintain a phase shift of 0 degrees, which results in a power factor of unity. So the components, then the environmental impact, all those things. It has come under the smart. The HVDC link also, like a generating station, receiving station, AC/DC station, and a DC/AC station, then transmission. So HVDC is also come under the smart grid. So dynamic power control, real-time monitoring and control, efficient transmission, interconnecting grids. Then we can say that a carbon neutral energy systems. So then WAN in smart grid system, wide area network. So then FAN, HAN. So with respect to the data rate, based on that we can use it. So WAN is the core technology in smart grid that contains the utilities, consumers, and distributed energy resources across the large geographical areas. Communication backbone is the WAN. So it connects the multiple NANs and LCDs, LDCs, and provide communication link for smart grid backbones. Real-time monitoring and control, high-speed transmission, technologies used like Ethernet networks, 3G, microwave transmission are used in WAN implementation. Then protection and control also, it is come under the smart grid, demand side response, load management, advanced metering infrastructure, energy storage systems. So the centralized server, a centralized server is called as a SCADA. So analyzes the information from smart meters and sends the commands to handle emergency demands, respond to changes, and protect the power grid. So smart grid security is important, and sometime recommendations include, so the performing risk and threats analysis early in the planning stages. So this is the distribution system in a smart grid, how they are implemented with respect to the WAN, LAN, and like that. So how it will be the control system, how it will be the transmission, where it will be the HV network, where it will be the MV network, where it will be the LV network, those things we can understand. So then volt bar war control, VBC enables the system operating in steady state by means of voltage and reactive power control, achieving through varying the generator voltage settings, changing the tap change settings of the transformer, and varying reactive power of a shunt compensator devices like capacitors and reactors. So the fault detection in smart grid, like failures in SG systems, components, cables and transmission lines, PV panels, wind turbines, power transformers, power converters, conventional energy systems. The section 3 indicates with the sensors and monitoring, like a smart sensor, smart meter, PMU, merging unit, VAMs like a SCADA, SMPS, AMI, cyber security in SG monitoring. The section 4 that indicates with SG communication infrastructure. So all those things, it has come under the smart grid only. So the detecting and locating the faults, and feature research and challenges that indicates with the integration of the ML. So and A and ML, how it will be, and for fault detection and implementation of the AI with then KNN, Marco model. Already I have discussed those things. So then the artificial intelligence, AI can be used to infer faults throughout the power grid. AI can be deployed in an Alivio accelerator to provide a high computing performance and throughput. The other methods for the fault detection in smart grids include impedance-based methods, analytical methods, and learning-based methods. Faults in smart grids are usually associated with abnormal electric currents, such as short circuits. It is important to detect fault quickly to prevent the network from breakdown. So here we can understand that the outage management of the smart grid. So the major functions usually found in an OMS include the prediction of the location of the transformer, fuse recloser or breaker that opened upon a failure, prioritizing the restoration efforts, and managing resources based upon the criteria such as locations of emergency, facilities, size of outages, and duration of outages. Providing information on extent of outages and the number of customers impacted to management, media, and regulators. Calculation of estimation and restoration times. Management of crews assisting in restoration. Calculation of crews requires restoration. So then the phase shifting the transformer. So that controls the flow of power in a three-phase electrification network. So they are the component in smart grids, helping to improve the stability and the flexibility of the power network. So coming to the plug-in electric vehicles. So the plug-in electric vehicle stands for, it is a type of hybrid electric vehicle that combines the traditional internal combustion engine with an electric motor and a rechargeable battery. So this plug-in electric vehicle offers a flexibility by allowing the users to run on electric power, gasoline, or a combination of. So these are the concept of electric and hybrid electric vehicles. Here it can be operated with a single source or multiple source, but we require the power electronics. So the control of the power electronics for optimal way, we require the AA tools. So the power, it may be the unidirectional or bidirectional. So the bidirectional means during the regenerative braking mode, the power is feeding to the source. So the different types of electric vehicles it can include with the battery electric vehicle, series electric hybrid electric vehicle, parallel hybrid electric vehicle, series parallel hybrid electric vehicle, plug-in hybrid electric vehicle, like that. So the battery powered electric vehicle is propelled by an electric motor only. Only one energy source only is taken on board, that is battery. And the advantage is zero emission vehicle, simple structure, and control of the traction system. So battery powered electric vehicle is an electric machine. It delivers mechanical power to load. The electric machine, that is the generator, obtains the mechanical power from load and charges the battery. So here you can see that it is indicates with a bidirection. And sometimes we can have the two energy source also. So how it will be, maybe the two power converters also. So one power converter which is used for controlling the generator side, the another power converter which is used for controlling the motor side, along with this one, the battery. So this is what the battery is an important source for the electric vehicle that transfers the energy from motor to wheels. So the primary electric vehicle powertrain that contains energy source, electric motor, and mechanical transmission. So it consists of electric power propulsion system and auxiliary system. So the electric propulsion system that indicates with the mechanical transmission, electric motor drive, electric power converter, vehicle controller, like that. So and this it will be includes with the energy management unit, vehicle controller, then energy source, like that. So the auxiliary power supply, steering unit control, AC control, that and all come under the auxiliary subsystems. So here it is shown with the different types of vehicles. like EV configuration with the clutch, gearbox, and a differential. The first one. Second one is EV configuration, mechanical differential replaced by using two machine electric motors. So the third configuration represents with the EV configuration without clutch and gearbox. So EV configuration with the wheel, motor, and mechanical gear, and EV configuration with the fixed gearbox and a differential, and EV configuration with wheel, motor, and no mechanical gear. Many configurations are there. So normally the torque density, we are based on the electric machines only, we are arriving the torque density. In general, we are preferring with respect to the high torque density, particularly the permanent magnet motors only will provide with the high torque density. That's why most of the places we are uh, preferring permanent magnet machines. So in the table itself, it is very clear. You can see that the permanent magnet motor only provides a torque to volume ratio, it will be more. The required features for the electric motor drives is high efficiency, good dynamic performance, high power density, low cost, then reliability, overload current capability, maintenance free, temperature resistance, fault tolerance, etc. The frameworks, we can say that a vehicle to grid, a grid to vehicle, and a vehicle to home, vehicle to vehicle, anything it may be possible. So this is the one of the configurations which we are using for a vehicle to grid. So grid to vehicle also it is possible. Vehicle to grid is also possible, provided we need to have the bidirectional power. And we can have it V2X, vehicle to load, vehicle to home, vehicle to grid, anything it may be possible. So the charging. So the Bell Power Solutions very recently has developed the chargers, the high efficient charger, so about a 94%, and the other chargers is also there. So the battery swapping technology includes the exchanging an EV discharged battery for charged one, eliminating the need to wait at the station for EV to charge. So the business model is based on the leasing, renting, subscription for the use of battery swapping stations or pay as you go systems for EV batteries. Advantages is there, but disadvantages many are there. But still it has to arrive the policy for availing this. These are the norms for chargers. Like 4 watts, the EV charging demand, based on the EV charging demand, how it will be. Fast charger, slow charger, medium charger, like that. And the site planning for EV charging is, site planning is an important aspect of integrating the EV charging in parking areas. It depends on the type of parking area, as well as the number and the type of EV charging points that need to be accommodated at the site. The space requirements, these are the standards. So the smart meters is also there, and the smart meters is a key component of the smart grid, which are uh, electricity networks that integrate the actions of consumers, generators, and the others to create the sustainable power systems. So benefits of the consumers, benefits of the utility communications, communication in home displays. So everywhere the smart grid, the smart meters come in within the home displays that provide the real-time feedback for the energy usage. So advanced metering infrastructure, real-time data, demand response, self-healing, and meter reading, all those things we can arrive. Then constrained application protocol is a lightweight protocol for communication between the devices with limited resources, like low power sensors. So message queuing telemetry, transport is a lightweight protocol, like a DLMS, a COSCM, then XMPP, we can use it. Then phasor measurement unit in smart grid. So then what it measures in the sense, the phase angle of the voltage and the current at a specific location of the power line. So this information can be used to determine the frequency and identify the system conditions. So the benefits is faster and more accurate than the traditional SCADA systems. So this is what IED, LAN in smart grid systems, and WAN in smart grid. So where we can implement. And I just want to conclude, since the topic is the AI-based smart grid systems. So one is the emerging trends and future directions in AI. So particularly deep learning techniques. The deep learning techniques as a convolutional neural network and recurrent neural networks have been used for power electronic systems, fault diagnosis and prognosis, energy management and control. Reinforcement learning has been applied for control optimization of power electronic systems. Edge computing, which involves processing the data at edge network instead of central location, has been used for real-time control and optimization of the power electronic systems. So hybrid AI system is a hybrid AI technique that combines multiple AI algorithms like fuzzy, neuro-fuzzy, like that. So the potential features that indicates with development of the new algorithms, integration with IoTs, then the standardization, data availability and quality, safety and reliability. So then opportunities that indicates with the development of the explainable AI, online learning, integration with the renewable energy sources, hardware optimization, system level optimization, like that. So thank you everyone for your patience and listening. Any clarifications about this lecture, you please ask me.
Dear participants, if you have any doubt, you can ask. So you can unmute your mic and you can ask to sir.
Sir, good evening, sir.
Good evening, sir.
Sir, basically, I have some basic doubts, sir. So actually, you have mentioned some battery storage by using a AI like this. Is there any specific value, sir? How much amount of a battery we are going to save? So that because we are having some analysis in that area.
Yes, correct.
See,
here the models, the AI tools, like I said that NN, meta-heuristic algorithms, the fuzzy logic. So how you are using for the energy storage applications. So for example, the solar PV system is there, your grid is there, and for example, or you can consider the standalone load. So the standalone load requires a certain amount of power. When excess power is generated, you can feed it with the energy storage device. That means you need to manage the power properly. So in this regard, we can apply with the AI.
AI technique. Okay. Maximum. So based on that method use only.
Yes,
so how much, what kind of method we are going to implement, then only we can justify the battery storage. Is it not?
Yes, correct.
Okay. Because we are just concentrating on this area only by applying some LoRaWAN techniques.
Only one information for you. Since you started to work in this area, you need to have the proper justification while using with AI-based techniques. AI techniques like machine learning or fuzzy logic or meta-heuristic methods. You need to justify properly. So how much the complexity of the system it is there in your system.
Yes, sir. Thank you, sir.
Thank you. Any other questions?
So the participants are asking whether they can get the PPT, sir. For the,
okay, madam. I will share, madam.
Okay, okay, sir. Thank you, sir.
Thank you, madam.
Okay, we can wind up the session. So a vote of thanks to sir. So on behalf of everyone present, I extend my sincere gratitude to Dr. S.Senthil Kumar sir for this enlightening session on AI techniques for power generation and distribution in smart grids. Your deep insights into the role of artificial intelligence in optimizing power systems, enhancing efficiency, and ensuring grid stability have given us a fresh perspective on the future of smart energy management. The way you bridged theoretical concepts with real-world applications was truly inspiring. We truly appreciate the time and effort you have taken to share your knowledge with us, sir. Thank you, sir, for your valuable contribution, and we look forward to much more such enriching interactions with you in the future. Thank you very much, sir.
Thank you, ma'am. Thank you, everyone.
Thank you, sir.
Thank you, ma'am. I'm leaving, ma'am.
Okay, okay. Thank you, sir. Thank you, sir.
Thank you.